Thank you. So yeah, I'm going to talk today about our work on fixing scalability issues of our points-to analysis. First, a bit of context. Our problem domain, his whole program points to analysis for optimizing compilers. So we implemented this analysis in the context of the GraalVM Native Image project, which is a new Java VM that takes your application together with the libraries, JDK, and the VM internals, all written in Java, or some language that compiles to Java bytecode, and feeds all of them together to a program analysis, a closed world points-to analysis, to prove facts about the code. And then the results of the analysis, we feed them into a ahead-of-time compiler. The results that we care about from the analysis are, first of all, the call graph construction, because of course we want to remove as much as possible of the code to minimize the size of the resulting binary. But we also want some specific fine-grained type information at certain program points to be able to do interesting optimizations, like call-side virtualization, null check elimination, or even removing types, fields from certain types that we know are unused. So in this context, what we need is a sound, precise, and fast analysis. I know, a lot of requirements. Unlike the analysis we heard about in the morning, ours needs to be sound because we cannot afford any false positives. Any false positive, it's imprecision in the compiler, which can lead to a crash at runtime. So we really want a sound analysis. It needs to be precise enough to justify the time you spent in the analysis for the entire compilation pipeline. So it needs to enable enough optimizations in the compiler, and needs to run fast. So this is part of a daily driver of many users that use this on their command line to modify their application a little bit, and immediately they want to see a fresh binary out of it. So we're talking about tens of seconds to maybe a few minutes, which in program analysis, it's quite fast. So why can existing analysis fulfill all of these requirements for us? First, on one hand, we have the context-insensitive points-to analysis, right, which happens to be precise enough for our case, but can have a quadratic behavior in practice. So for a program with V variables and heap abstractions, where here for heap abstraction, I mean it's the static model of a dynamically allocated object at runtime, you get OVN complexity. Right? So for large enough programs, that becomes a huge problem. Unfortunately, most standard Java benchmarks like spec, JVM, and DaCapo are too small to exhibit this behavior, but real-world Java applications have a huge problem there. On the other end of the spectrum, we have the rapid type analysis, which avoids this quadratic behavior because it doesn't need to model each variable individually. It instead starts with the set of reachable methods, finds what types are allocated, infers more reachable methods, and so on iteratively until it reaches an endpoint, and that solves the scalability problem. So you grow linearly with the application size, but you lose significant precision. So the question we asked ourselves was, can a context-insensitive points-to analysis grow linearly with application size while still maintaining soundness and most of the precision? And the answer for that is yes in our case. So let me plot the analysis I just mentioned here. We're looking here at, on the x-axis, at the reachable methods after the analysis finishes and the compiler removes all the unreachable code. And on the y-axis, we have the analysis time. For the rapid type analysis, of course, we see the expected linear behavior. Here we're looking at 7 benchmarks from various sources, the biggest applications we could find. At the very right, it's a Renaissance benchmark suite benchmark based on the Spark framework. Then the 3 bigger ones in the middle are 3 modern Java microservices frameworks like Spring, Micronaut, and Quarkus. And then to the left, there are a few more benchmarks that are representative and we extracted from related work. So then when we plot the points-to analysis, you can already see the problem starting at about 100K, right? And then the more you have to analyze, the bigger it gets. Here we have almost 5x difference for the biggest benchmark. Here it's important to notice that the lines on the points on these lines are a bit to the left in the case of the points to analysis, because of course the points to analysis has better precision, can prove more unreachable methods and remove them from the graph. And then the last line, it's our analysis. Our analysis has the same linear behavior as the rapid type analysis, while preserving most of the performance of the precision, of the points to analysis. So then we call this analysis a type-based points to analysis with saturation. So what does that mean? So first of all, we use a type-based analysis, points to analysis. Unlike traditional analysis, we don't take into account the specific allocation site of an object. We just care about the type. The type is essential to enable optimizations like call site virtualization, to maintain field sensitivity, and so on. But moreover, the call site is in general lost to, when you analyze Java features like unsafe and Java native interface, once you pass an object from the Java world to the native world, you lose all the precision, because for soundness reasons, you have to assume that all objects of the same type are aliasing. So you lose all this call size allocation size sensitivity anyway, so we remove it from the beginning. And the second step is using this idea of saturation for the variables in the points to graph. So the insight here is that if the compiler cannot use an analysis result to drive further optimizations, then the time spent proving that result is not really well spent, right? So in our case, we just want to preserve precision where it matters, just enough to enable these optimizations. So we track a small number of types for each variable. If you can prove that one variable has one type, that's great. You can do devirtualization, you can do type check elimination, and so on. If you have a small number of types, then you can still do some polymorphic inlining and so on. But then once you get into 10, 20, 200, 2000, it doesn't really matter for the compiler, because those results are virtually equivalent from a practical standpoint. So to go a bit more detail with this saturation idea, so what we do precisely, we set a maximum size for each type state, right? When we exceed that size, we just call it saturated. So then the points to analysis no longer needs to track concrete information for each of these variables, and instead we fall back to declare type information. This is information that we get from the compiler, from the source code. So then a saturated variable can have any reachable subtype of its declared type, right? So then when new types become reachable for that declared type, you get the precision for free for that variable. You don't need to analyze that variable independently anymore. So this is what, the declared type information fallback is what allows us to preserve most of the precision. And the second, once a node in the pointer assignment graph gets saturated, then you can simply remove it. And then more importantly, you can propagate, and you have to propagate for correctness, this saturation signal along all the use edges. Because all the dependent nodes, they cannot rely on the saturated node to give further analysis types in the analysis, which has the side effect that reduces the size of the graph quite a lot while the analysis is running. So you reduce analysis time by not having to analyze as much anymore, and you reduce the memory footprint of the entire analysis. So then, if we go back to talk about complexity, now we're looking here at complexity of type-based points to analysis. So the second variable this time is types, but it's still quadratic in practice. Now with saturation, the second variable becomes a constant. So your complexity becomes linear in number of variables, so application size. So all of a sudden you have a nice algorithmic property of the analysis that you can rely on. I'm not going to cover the formalism of the analysis, how saturation fits with the traditional analysis. That's all in the paper. But instead, I would like to look at the code example here. So here we have a simple main class that has two objects, O1 and O2. Each of them returned by two source methods, source1 and source2. And then on each of them, we call toString. ToString in Java, it's a method declared on the base type. So it's on the object type, which is the base type of all the other types in the system. So these two call sites have the potential of being highly polymorphic. So then source 1 always returns an A and implements toString. Source 2 loads a value from an object array and returns that to its caller. So then, we parse this code. We build our type flow graph, where each node in the graph models one of the operational objects. They are linked with use edges that propagate type information to their successors. And the new instance node is a source of value of type in our case in the analysis. So source 1 and source 2 methods are immediately resolved statically. So they are immediately linked into the interprocedural graph. And then when we analyze new instance A, we propagate that type information along the use edges all the way to this virtual call. And here we can resolve the concrete callee A toString. We link that in the caller, the parameters and the return type, and propagate the type further in the in the callee and all the other callees. And then we propagate the return type back to the caller. So at the end of this phase of the analysis, we can already prove that O1 has a single concrete type, which is A. Using that information, we can eliminate this implicit null check. In Java, all the visual method calls have an implicit null check. So here we track nullness information, so we know this can never have a null pointer exception at runtime. And moreover, we can simplify this virtual invoke. We can optimize it to a static invoke or direct invoke because we know that this is the only callee possible at runtime, right? That can in turn enable some inlining of this method and so on. But now, when you look at the second half of the example, things get a bit more complicated. Unfortunately, in Java, object array, it's a huge source of unpreciseness for analysis because most collections use an object array internally, and objects array are going to alias in practice unless you use a very, very deep context in your analysis, which is not really practical. So when that happens, most likely the value you get out of here has a huge type state, right? It's going to have thousands of types in a big enough application. So that means this value is already saturated from our point of view, which means that, we mark it as saturated, and we propagate that signal across the use edges all the way to the virtual invoke, and all these nodes are now removed from the graph. But then what happens when you remove a virtual invoke from the graph? Well, for correctness, you have to add in place another construct, which in this case, it's a global per application virtual invoke that models all the virtual invokes that were saturated on the same target method, right? So then this is linked to all the possible callees at this call site. It transmits all the possible types, back to the return of this method, which maintains the soundness of the results of the analysis. So after this second phase of the analysis, unfortunately, O2 cannot be optimized. You cannot prove anything about its type, but you don't waste time in the analysis trying to do that by propagating types here continuously. So we simply cut off this part of the graph and continue the analysis in other parts where it's more productive. Here it's interesting to notice that although the formal receiver can saturate, the type checks inside toString method can actually allow the formal return to still maintain its precise type information. So saturation propagation across use edges stops where you have enough filtering information. And then as the last thing I want to cover is one of the results from our benchmarks in more detail. I'm using here Spring Pet Clinic. It's one of these microservices frameworks from Java, which only has 200,000 methods. So it's not our biggest benchmark, but the performance profile, it's a bit nicer to look at because there is not such a huge difference between the numbers we get and the default numbers. So I plot here the rapid type analysis and then the context-insensitive type-based analysis with saturation between 0 to 2048. A context-insensitive analysis for looking at the performance, but we also measure a context-sensitive analysis. Here we don't care about the time because, of course, the time goes out through the roof, but what we care about is the precision, like what would be the best precision we could get with the best analysis we can implement. This one is a standard 2-object, 1-heap analysis from the literature, which is implemented in the same framework. So Then for the metrics we care about, we actually look at the compiler results after applying the analysis results, right? We don't immediately look at the analysis results because what's more interesting for us is, okay, what can I do with these results? So we look at type checks, also null checks, polymorphic calls, and the call edges, how big is the graph after the compilation. Here for type checks and polymorphic calls, we don't have the numbers for the rapid type analysis, but if you set a threshold of 0 for saturation, you essentially degrade the points to analysis to a rapid type analysis in practice when it comes to precision. Performance-wise, you still pay a bit of penalty because you need to track your type flow graph initially. But here we can see that already in the first few hundreds of saturation threshold, we get more than 2x improvement in analysis time for this benchmark, while improving precision quite a bit in all the metrics that we care about. And one last point I want to make is that context-sensitive analysis, although you spend so much time when you want soundness, is not even give you that much precision. Because if you want to model unsafe Java native interface soundly, then you lose all that precision when you have to over-approximate, because you cannot ever afford to under-approximate. And that concludes my talk, and I hope we have time for questions. Thank you.
Yes, questions, please.
Hi, it was a really cool talk. I just had a question about your last slide.
Mm-hmm.
For type checks, what are those? Are those due to downcasts or array stores or just everything like that?
Everything, also the implicit type checks. In Java, sometimes you have implicit type checks, so not only the bytecode ones.
Like what's an implicit type check?
You can have a check cast. You can have and then you can have for for field accesses.
Okay.
But it covers all the type checks.
It covers all the kind of dynamic type checks.
Yeah,
that happen.
exactly.
Okay, thank you.
Hello, very interesting. Would it make sense to do a quick pre-check whether you have any native method that you're calling? Because if you assume a program analysis framework that uses summaries to abstract from API behavior anyway, the only question is whether you have native code inside the user code, and then you could just check over it whether there is a native method declared or not, and in that case you wouldn't need that over-approximation anyway in the first place.
Sure, you could do that. You could have type descriptors at native calls, but all in all, you're going to have some native calls somewhere. And because you have so much aliasing, you cannot prove that an object only, it's collocated in a certain part of the application. Most likely, it's going to escape anyway.
Yeah, I was just imagining if you're using summaries for the API calls, right? In that case, you're getting rid of all the JDK implementation anyway because it's stopped away for performance reasons. And then I could imagine that there are applications that just have no native code left at all.
That is not true. So in this project, we are actually putting together the entire JDK, which uses heavily unsafe and GenI calls, and that's...
I know that my model was slightly different, kind of. I don't have the JVM, I put that into summaries on models as well, so that I just analyze the application. Then I was thinking if I could use what you have presented and take it even a bit further because I can constrain my model.
Sure, but then you need to really model the behavior of the JDK in great detail unless you don't allow any object to cross the boundary between the application and your model.
Let's take this offline. There are approaches for actually summarizing JDK methods.
Yeah, so in that case, of course, you could improve the precision a bit. But in our case, we want the JDK to be analyzed together with the application. Mm-hmm. That's the whole point, to remove unreachable code in the JDK. Because at runtime, you want the minimal footprint and instant startup for the binary.
Okay, thank you.
All right, thanks for the nice talk. So it looks like here from these graphs, right, that the analysis time kind of is basically the same regardless of size, and then the precision kind of bottoms out, at 1,000, 2,000 for this particular benchmark. But would that vary depending on the benchmark, like what size you need to saturate to?
So there are all the details in the paper, of course. In general, we found out that the range for the saturation threshold is quite wide. As you can see here, already around here, you can get all the precision benefits. for pretty much the same budget. So it doesn't vary that much. So, but what it's constant in our benchmarks for the same size is this ratio here between a saturated analysis and a context-insensitive analysis that doesn't do that.
Thank you.
Right, let's thank the speaker again.
Okay.